All right, now we're looking at chapter 1.6. This is the last section in chapter 1, and we're going to be talking about inverse functions. So let f and g be two functions such that f of g of x equals x. So this means the composition simplifies to x for every domain in for every x in the domain of g of x. In other words, the inner function. Remember when we did composition, we always wrote down the inner domain. And vice versa. G of f of x also has to simplify to x, and that has to be true for every x in the domain of f of x, which again is the inner function. Under these conditions, function g is said to be the inverse of f and vice versa. And instead of always calling them f of x and g of x, we can say, well, if g is an inverse function, then it's denoted by this. It looks like f to the negative 1. This is read f inverse. And just quick notation here. F inverse of x does not mean 1 over f of x. It means inverse. So we have to be careful with that. We will never have function notation with a negative exponent that means what a negative exponent means. Okay, so the third piece of this, it has to be true that the range of f equals the domain of the inverse, and the domain of f has to equal the range of the inverse. So I usually do something like this. We have domain of f and range of f, and then we have a domain of f inverse and a range of f inverse. So the domain of f has to match the range of f inverse, and the range of f has to match the domain of f inverse. All right, so show that the functions are inverses, verifying algebraically. So here's what you have to do for that. We have to show these 3 steps. We have to show both compositions and checking domain and range. So step 1 is f of g of x. This is supposed to simplify by x if these are 2x, if these are inverses. So this becomes f of the cube root of x plus 1 over 2. Plugging that into f's function. When you raise a cube root to the 3rd power, the root and the power are going to cancel out. Okay, so that's going to become 2 times x plus 1 over 2 minus 1. And now we're down to algebra stuff. So this is 2 over 1, right? So this 2 can cancel with this divided by 2. X plus 1 minus 1 does simplify to x. So far, the first piece of the definition is true. And then we need to do composition the other way. It could be that composition works one way and not the other. So g of f of x is g of 2x cubed minus 1. And so g's function is the cube root of x plus 1. So we're going to put in for x 2x cubed minus 1 plus 1 all over 2. This simplifies to just 2x cubed over 2, right? Minus 1 plus 1 goes away. Those 2's divide out to 1. The cube root of x cubed is x. Now this one is not absolute value x. That rule is only when you even root something to an even exponent. Okay, so far, 1 and 2, those parts of the definition are satisfied. And the third thing we need to do is check domain and range. So I always just set it up like this because that's just the visual I have in my brain. So domain of f, range of f, and instead of f inverse, let's call it domain of g and range of g, since we have f of x and g of x. F of x is a cubic, so its domain and range are all real numbers. And g of x is a cube root function, which remember we can plug anything into that as well. So that domain and range is also all real numbers. And so it is true that domain of f equals range of g and vice versa. All right, so because we've shown all 3 of these parts of the definition of inverses, we can finally say f and g are inverses. Now, we have to show work. Even if you can do this composition in your head and know that it comes out to x, you've got to show that the functions are inverses. So you do need to show probably 2 steps like I did. for the simplifying, even if it's kind of obvious to you. It's kind of like a little algebraic proof. Okay, start with f of g of x, which means f of square root of x, which means the square root of x squared. Now this is not absolute value of x. That's the other way around. When we square root x squared, that's absolute value of x. When we square a root, we just get the thing underneath. Okay, so that's x. Good. And if we go the other way, g of f of x means g of x squared. So this is that scenario I was talking about, square root of x squared. It's actually not just x, it's absolute value of x. So I could stop here and say this didn't simplify to x, this simplified to absolute value of x. That's different, right? Because just x can be positive or negative, but the absolute value of x will always give me a positive answer. But maybe I forget the absolute value, so let's also show that, so I'm just going to put an x right here. Let's also show that domain and range isn't satisfied. So start with the domain and range of f. F is quadratic, so its domain is all reals. And the range, remember this would be a parabola that opens up, so its range is 0 to infinity. The domain of g and the range of g. So the domain for our square root function, whether you think about the graph or the rules, the domain is 0 to infinity, and the range is also 0 to infinity. So even though this diagonal matches, the range of f does match the domain of g, right here, the domain of f is not equal to the range of g. So that's another reason. 2 and 3 conditions were failed. Now, like I said, you can stop after 2. You don't have to show me domain and range. As soon as one of the compositions fails, you can say f and g are not inverses. All right. What about the graph of an inverse function? So there is a relationship between inverse graphs. The graph of f of x and its inverse function are related so that the point on f of x that has the point AB, on the inverse function, flip the x and y, the reverse, BA, has to be on that graph as well. And what that is a reflection in the line y equals x. So here's the line y equals x, just a line with a slope of 1 going through 0, 0. And yeah, every point on either of these graphs can be reflected across that diagonal line, and you get a point that lands on the other side. Okay, so easy, quick question. Write the ordered pair that must exist on the inverse function graph. So if the point -2, 5, that's your A, B, is on the graph of f, then f inverse must contain or must have BA 5, -2. That's it. We don't need the equation. We know that the graphs have that relationship. Okay, here's a practice AP question. The graph of the piecewise linear function f is shown in the figure. Let g be the inverse of f. What's the maximum value of g? So maximum value is the highest y value. It would probably be good for us to sketch the graph of g. So if you can picture it, you can say, there's this, reflect this across the axis, across the line y equals x, but I'm not much of a visual person, so I would just give a quick, these are the points on f, and then I'm just going to flip them and plot them. So 4, 5, 5, 7. So for g, the graph is 0, 0, 3, 3, 5, 4, 7, 5. And we're looking for the highest y value. So I can see it right here, but you can kind of quickly graph this too. It's not too bad to graph. So G's graph looks like this, which remember we said should be a reflection. See, my reflection line was kind of poor. Here we go. Should be a reflection across that line, y equals x. So yeah, what is the maximum value? The maximum y value is right there. It's 5. All right. One-to-one function. This is just a bit of vocab. A function is one-to-one when for a and b in its domain, f of a equals f of b implies that a equals b. So what does that mean? That means there are no points with same y value. Okay, let's think about why this might be the case. So the key is that a function is one-to-one. A function is one-to-one if it has an inverse function. Okay, so what about this? We just said that back here, x squared didn't have an inverse function with square root of x, which seems kind of strange, right? But if we think about what this is saying, okay, so this graph is saying, what if we have a point at A and a point at B, and they have the same height? So maybe some sort of, let's just do a parabola just for simplicity's sake. So here's f of A, here's f of B. Okay, now think about those points. Let me make up a point for this. Let me say this is 2, 4, and this one's negative 2, 4. So what would the inverse graph look like? If this is f, what would the inverse graph look like? Well, we know it would have 0, 0 on it. It would have 4, 2. So let's see, this is supposed to be 2 and negative 2. So it would have like, get my labels all correct. It would have like 4, 2 on it and negative, let's see, and 4, negative 2, like this. So it would be like, this is such a bad sketch, but you get the idea. It would be something like this, right? Those are a reflection across the line y equals x. But the key is that the blue graph represents an inverse, but not an inverse function. This graph, the inverse graph, fails the vertical line test. So it's not a function. So can I create an inverse graph? Yes, I can always create an inverse graph by flipping A and B points, flipping the x and y coordinates, but I can't always create an inverse function. Okay, so how do we figure this out quickly without like actually sketching all these graphs and plotting the reverse points and thinking about what happens? In comes the horizontal line test, which I'm going to be calling HLT. It's a quick way to decide, based on the graph, whether there's an inverse function. If you look at this graph for f, if I can draw a horizontal line through any 2 points on the graph, this fails HLT, and it means that there's no inverse function. We can always figure out what are the inverse operations, which we'll talk about, but there's no inverse function for that. If you did flip your x and y coordinates, the thing that you're left with would fail the vertical line test. Okay, so what if we are looking at finding an inverse function? Like now we know how to kind of visualize whether or not an inverse function exists, but if an inverse function does exist, how do we find out what it is? They're not always going to give you f of x and g of x to check. Sometimes they'll say, here's f of x, find the inverse function. Okay, so first of all, be sure an inverse should exist. So I usually think about the graph, if it's kind of a basic graph, and then I think about HLT, is it passing or not? If the graph does pass horizontal line test, then step 2 is let's get rid of the f of x and just replace the equation with y. Why do we do that? Like this. Because we're going to be rearranging variables, and it's just easier to have a y instead of an f of x in all of your work. Okay, so there's that. Step 3 is interchange the roles of x and y. So this is what I call the inverse step. Because remember, the graphs have this relationship. The graph of f and its inverse have the x's and y's, the domains and range are switched. So this step means just make it x equals 5 minus 3y all over 2. And we need to solve for y. So once you flip this thing, use the correct steps for equation solving to solve for y. So I've got to multiply 2 over. It depends on how you want to show this. I like to add 3y and subtract 2x. It's totally fine to subtract 5 to the left side too, but that just gets rid of a negative in front of my y. Then I divide everything by x, which would just look like this. Otherwise, you would make it 5/3 minus 2x over 3. Okay, and then step 4 says replace y with f inverse of x. And finally, we just created a new function, so we need to make sure that we write down any domain restrictions. Now, a line does not have domain restrictions, but here's how I figure out the domain. Be sure to restrict, if needed, the domain for f inverse. Here's the domain for f inverse. It should always be the range of f becomes your domain. So it's not a decision for you to say, do I need a restriction or not? You're saying back here, this is linear, right? Linear function has a domain of all reals. That has to carry down in, has a range of all reals. Has a domain too. It has a range of all reals. That has to become the domain. So all real numbers for our x value. And I should have said this. I didn't do step 1. This graph passes the horizontal line test because it's some sort of line, right, with a y-intercept of 5 over 2 and a negative slope of some sort. So that passes horizontal line test. Let's start with horizontal line test for number 5. So a square root function, you don't have to get deep into the transformations. It's just the fact that this is some sort of square root function, which passes the horizontal line test. So we can replace g of x with y. And maybe you don't write this step. Maybe you get right down to the switching step. That is okay with me. And then we need to solve for y. So we're going to square both sides, get rid of the square root. Add 3. Divide the whole thing by 2. This becomes g inverse. G inverse of x equals, I just like having it on this side, x squared plus 3 over 2. Now, what about the domain? Is the domain going to be all reals or not? Well, remember, you have to figure out the range of g first. What is the range of this graph? 0 to infinity. That needs to become the domain of my inverse function. So x should be greater than or equal to 0. Remember, range is y greater than or equal to 0. So what we've done is flip, trade out y for x, just like we do with inverse functions. This makes sense because this is a half of a parabola, right? The reflection across line y equals x for this graph should look like a half of a parabola. It's going to be something like this. Okay, number 6. Speaking of half of parabolas, we have a quadratic. Normally quadratics do not have inverse functions, but this is saying only look at this graph for x values less than or equal to 0. So x squared minus 5 is a parabola that's been shifted down 5, but you're only on the left side of it. So half of a parabola passes the horizontal line test. All right, so y equals x squared minus 5. X equals y squared minus 5. X plus 5 equals y squared. Normally when we square root both sides, we put in a plus or minus, right? We can't have both plus and minus though. Our inverse graph needs to be only a reflection of the values that are on this h of f graph, right? So if all of the x values started out less than or equal to 0, then all of the y values need to be less than or equal to 0. So I need to choose the negative square root of x plus 5. Right? Because if the x values are negative, when I flip all of these x and y points, I'm only going to get negative values for, it's going to be something like this. I'm only going to get negative values for that square root graph as well. So let's call this h inverse of x. It's negative square root of x plus 5. And then what about the domain? So what's the range of h? My h graph, let me get my green part off there. What's the range of h? The h graph goes from negative 5 to infinity. In other words, the y values are greater than or equal to negative 5. So that changes to x values here. The x values need to remain greater than or equal to negative 5. Or you can use interval notation as well, negative 5 to infinity. Number 7, think about this graph. This is one that I've asked you to memorize. This has shown up on 3 or 4 assignments now. So if you don't know this graph yet, get to studying, please. This is a semicircle. The radius is based off of this number. Square root of 100 is 10. So this gives me all kinds of information about domain and range. Does this graph pass the horizontal line test? No, it does not. So there is no inverse function for j of x. So we do not have to go through the trouble of figuring anything out for that. All right. That's it for today's notes. If you have questions, please come to office hours and I will try to help you out.